So this is biochemical assays. So earlier we talked about the biophysical assays, which are mainly used to determine binding capacity. The binding assay, which mainly determines the binding assay. So the biophysical assays cannot tell us any functional change within the protein domain or within the structure that the protein is activated or inhibited. But in biochemical assay, we can detect any functional change. So depending on our approach or our library type, we can use biochemical assays, but ultimately we have to use a cellular or cell-based assay at last. But to get an initial idea, we can use biochemical or biophysical assay, but we cannot solely rely on this one assay or one type of assay, biochemical or biophysical, but we have to use a cell-based assay in order to get a good result, robust result at the end of this heat to lead phase. So biochemical assays are artificial system. It only involves our target protein. So it does not have the other cellular compounds, for example, nucleus or ribosome, etc. It only involves our target protein and target enzyme that and all the other chemicals or enzyme that is involved in the pathway or the reaction pathway. So it only captures the key interactions. So as I said, we cannot solely rely on this one test or assay to evaluate our hits. So, like all the assays, this biochemical assay must be robust and reproducible and high throughput, and they provide functional data. Yes, I mentioned about functional means functional change, and it is also important at some stage that this translates into effect in a cell assay. Yes, we have to finally transfer this or translate these results into a cell-based assay for further confirmation, where the endogenous target protein and biological we can see biological response in the cellular or cell-based assay. But this biochemical assay is quite useful at earlier stages of, if we have more hits, then we can simply quickly use biochemical or biophysical assay to see any functional change. So here are the criteria of assay development: highly specific interaction, only the protein is involved, protein of interest or target interest. So no other system is involved, like no other cellular machineries are involved. Reproducible, that means we can design or we can get the same data or same parameters, so that we can use this technique in the same parameter, same manner, so that we can get close data after weeks or months. So variation must be low enough to clearly identify response. So this variation we measure by a Z factor, which is a statistical approach. So the Z factor determines the variation of the results. For example, if we test five tests of one hit 5 times, then it should give the same result. So the variation should not it should not vary much. So the Z factor should be low. So like all the assays, the Z factor determines the variation and the noise from background noise to the actual result. So yeah, like if we test our heat at 5 nanomole 5 times, then the results we get should have close to the, for instance, if we get 50% signal, so if we test 5 times, so then it should range from 50% to 45% or 48%. So it should not vary like 50% in one test and 30% or 20%. So then the assay is not robust or reproducible. Then we cannot select those assay. So the problem is within that assay. So positive control, like like every experiment we use positive and negative control. So here we use positive control. That means we deliberately use a positive hit or positive drug compound that will inhibit, that we know that surely gonna inhibit with our target so that we can get a positive result. So it's like a positive confirmation, positive control. And low false negative, so it is quite important, because if our assay gives false negative results, that means it cannot capture good molecules that would bind. So it cannot detect the actual compounds, so it gives a negative result of those compounds, but actually those compounds were binding, so we cannot miss those good compounds. So false negative, we have to reduce false negative results. So false positive would if our assay have false positive but low false negative, that would be acceptable, because false positive means those compound we are getting that were not that much good or a strong affinity, but if we have lot high false negative, that means we are missing valuable good drugs. So in that case, if our assay has some level of false positive, that would be acceptable, but we cannot accept high or moderate negative result, false negative results. So that's why the criteria of biochemical assays. So moving to the next slide. So here is an example of a biochemical assay, that is fluorescence depolarization assay. So in this biochemical assay, fluorescence depolarization assay, it is simple and rapid method to measure protein ligand interaction. So if our target is a kinase enzyme, kinase is a protein, the function of a kinase is to transfer ATP, transfer phosphate group, or the function of kinase is phosphorylation. So it mainly transfer phosphate group to another substrate or another enzyme or another target in the presence of ATP. So kinase is a phosphorylation enzyme that transfer phosphate group. So if our target is a kinase enzyme, then we use a substrate. Substrate is a, like, substrate means any other molecule that binds to it, that is the substrate. So our substrate is a fluorescence tagged substrate, and the function of a kinase enzyme is to transfer phosphate group with in the presence of ATP. So if our goal is to find hit compounds that would prevent this kinase enzyme. So if our hit ligand inhibits this kinase, that means the phosphorylation would not happen. So what happens normally in the absence of a good inhibitor? Normally the kinase transfer phosphorylates to our substrate, and then this phosphate substrate, this phosphate grouped substrate will bind to a bead, IMAP beads. So upon binding to the beads, so in the assay there are beads, so bead mainly binds to the substrate that have phosphate group, phosphorylated substrate. So upon binding to the beads, so it gives high signal, high polarization. But if our ligand, or if in the presence of a good ligand, the ligand will inhibit our kinase, so that kinase will not function, and so that the function so the kinase will not transfer phosphorylate group, so our substrate will remain in this phase. So in this phase we will get a low polarization, a low signal. So we can get an idea by measuring the polarization, so which compound are good. If we add one compound, and if we get a high polarization to our assay, that means that compound is not good or not binding to our assay. So if we add another hit and we get low polarization, that means our target is inhibited, and we get a low signal. So here is the function of the phosphokinase. And IMAP beads are, like, traditionally we used uh, radioactive assays, which are quite dangerous and expensive radioactive assays, and we also use antibody based assays. So antibody based assay also have severe limitation because it interferes with the kinase and other, so we don't want those assays. So IMAP is like non-antibody, non-radioactive, non-antibody based assay. It is like it uses metal, trivalent metal, so it is nowadays quite getting familiar. So here is some function of the kinase. In cancer setting, most of the mutations happen in kinase, and kinase enzyme has a very crucial role because it activates several. If one kinase get activated, mainly it phosphorylates one enzyme or one target, then it initiates a chain or a cascade of reactions. So one kinase can influence thousands of key molecules within a interlinked pathway. So in that cancer setting, a lot of kinases are abnormal or mutated. So most of the time, our target is kinase enzyme in cancer, a lot of cancers. And a number of drugs are kinase inhibitors like imatinib or erdafitinib. The last suffix, the nib, anib refers to those kinase inhibitors. So here we gave one example of the biochemical assay, but there are a lot of useful biochemical assays. For example, FRET, FRET FRET assays, and TR FRET, and the other lot of other biochemical assays. Those are very complicated. So this is a quite simple biochemical assay.